For any help-related queries, call us at +1 678 648 4277. You can mail us at support@mathhomeworksolver.com or reach us at https://www.mathhomeworksolver.com. Problem 1. 1. A real number r is called sensible if there exist positive integers a and b such that, for example, setting a equals 2 and b equals 1 shows that square root 2 is sensible. Prove that 3 square root 2 is not sensible. Consider only positive real roots in this problem. Solution. The proof is by contradiction. Assume for the purpose of contradiction that is sensible. Then there exist positive integers a and b such that squaring both sides of this equation gives a /b equals, which implies that is rational. Since is rational, we can write it as a fraction x/y in lowest terms, where x is an integer and y is a positive integer. Therefore, we have in the last equation, the left side is even, and so the right side must be even. Since x3 is even, x itself must be even. This implies that the right side is actually divisible by 8, and so the left side must also be divisible by 8. Therefore, y3 is even, and so y itself must be even. mathhomeworksolver.com. The fact that both x and y are even contradicts the fact that x/y is a fraction in lowest terms. Therefore, is not sensible. Problem 2. Translate the following sentence into a predicate formula. There is a student who has emailed exactly 2 other people in the class, besides possibly herself. The domain of discourse should be the set of students in the class. In addition, the only predicates that you may use are equality and x, y, meaning that x has sent email to y. Solution. A good way to begin tackling this problem is by trying to translate parts of the sentence. Begin by trying to assert that student X has emailed students Y and Z, X, Y, X, Z. Now we want to say that Y and Z not the same student, and neither of them is X either. mathhomeworksolver.com. Now, we must think of a way to say that the only people X might have emailed are X, Y, and Z, S, X, S, minus S equals X, S equals Y, S equals Z. Finally, we can say there is some student who emailed exactly 2 other students by existentially quantifying X, Y, and Z. So the complete translation is X, Y, Z, X, Y, X, Z, 1. S, X, S, minus S equals X, S equals Y, S equals Z, 3. Problem 3. Express each of the following predicates and propositions in formal logic notation. The domain of discourse is the non-negative integers, n. In addition to the propositional operators, variables and quantifiers, you may define predicates using addition, multiplication, and equality symbols, but no constants, like 0, 1. For example, the proposition n is an even number could be written m plus m equals n. N is the sum of 3 perfect squares. mathhomeworksolver.com. Solution. X, Y, Z, x plus y plus z equals n. Since the constant 0 is not allowed to appear explicitly, the predicate x equals 0 can't be written directly, but note that it could be expressed in a simple way as x plus x equals x. Then the predicate x greater than y could be expressed. Y plus w equals x, w equals 0. Shown how to express x greater than y, it's okay to use it too. Note that we've used in this formula, even though it's technically not allowed. But since is equivalent to the allowed formula, w plus w equals w, we can use with the understanding that it abbreviates the real thing. And now that we've x greater than 1. Solution. The straightforward approach is to define x equals 1 as y, xy equals y, and then express x greater than 1 as y equals 1, x greater than y. C, n is a prime number. MathHomeworkSolver.com. Solution. Is prime n equals n greater than 1, x. Y, x greater than 1, y greater than 1, x, y equals n. D, n is a product of two distinct primes. Solution. X, y, x equals y, n equals x, y, is prime, x, is prime, y. E, there is no largest prime number. Solution. Of course this is a true statement, so it could be expressed by the logically equivalent formula 1 is equal to 1, but even if we didn't know this, we could transcribe the statement directly as P is prime, P, Q, is prime, Q, minus P greater than or equal to Q, F, Goldbach conjecture, every even natural number n greater than 2 can be expressed as the sum of two primes. Solution. We can define n greater than 2 with the formula y equals 1, x greater than y plus y. Likewise, n equals 2k can be expressed as n equals k plus k. Then we can express the conjecture with MathHomeworkSolver.com. n greater than 2k, n equals 2k minus p, q, is prime, p, is prime, q, n equals p plus q, g. Bertrand's postulate, if n greater than 1, then there is always at least one prime p such that n less than p less than 2n. Solution. n greater than 1 minus p is prime, p, n less than p less than 2n, problem 4. If a set A is finite, then A less than 2A equals p A, and so there is no surjection from set A to its power set. Show that this is still true if A is infinite. Hint, remember Russell's paradox and consider xax/fx, where f is such a surjection. Solution. We prove there is no surjection by contradiction. Suppose there was a surjection f, a p, a, for some set A. Let w xax/ not f, x, so by definition. For all x a. But wa by definition and hence is a member of p, a. This means w equals f, a, for some a, since f is a surjection to p, a. So we have from for that xf a x/f x 5. MathHomeworkSolver.com. xw x/not f x. For all x a, substituting a for x in 5 yields a contradiction, proving that there cannot be such an f. Problem 5. A. Prove that z, p, z, q, z minus x, p, x, y, q, y, 6 is valid. Use the proof in the subsection on validity in week 2 notes as a guide to writing your own proof here. Solution. Proof. Assume z, p, z, q, z. 7, that is, p, z, q, z holds for some element, z, of the domain. Let C be this element, that is, we have P, C, Q, C. In particular, P, C holds by itself. So we conclude, by existential generalization, X, P, X. We conclude Y, Q, Y, similarly. Hence, X, P, X, Y, Q, Y, 8. MathHomeworkSolver.com. Holds. This shows that 8 holds in any interpretation in which 7 holds. Therefore, 7 implies 8 in all interpretations, that is, 6 is valid. B. Prove that the converse of 6 is not valid by describing a countermodel as in week 2 notes. Solution. Proof. We describe a countermodel in which 8 is true and 7 is false. Namely, let the domain d, b, pi, e, p, x mean x equals pi, and q, y mean y equals e. Then, x, p, x is true, let x be pi, and likewise y, q, y is true.